Right, hold your breath, everybody. Hi, can you see me? Yeah, guys, thank you so much for your feedback because you couldn't see my face. And then, like seconds after the end of the lesson, Eleanor Wynne, your dad, got in touch and said, "Oh, you should use this software, and it's free." And here I am. Thank you, Eleanor. We also had some excellent feedback from Zach and Henry, who said it was good, but there were no stories. Like, we just had to learn for half an hour with zero stories. Lara, we can't learn in these conditions. So, Zach and Henry, thanks to you, we have got a little on screen story time today. So, should we get going? Last year, 2019, was the 150th anniversary of the periodic table existing. We learned about last week how everything in the whole world is made out of atoms. They're like the ingredients of everything in the world. And there's 118 different atoms that we know of. And if you break like gold in half again and again and again and again, and again, you are left with just one atom of gold. If you break I don't know, loads of stuff, iron in half again and again and again, you're left with an atom of iron. If you break water in half again and again and again, you will be left with one oxygen atom and two hydrogen atoms stuck together. And if you break that in half again, then you end up with you don't have water anymore. You've just got two particles of hydrogen and one particle of oxygen. So the periodic table is a table of elements. Anything which is only made of one kind of atom is an element. So oxygen is an element, hydrogen is an element, water is not an element because it's got more than one atom in it. All right. Some of the symbols are really obvious, like hydrogen is just an H. The whole of the second period, boron, carbon, it's just buffer boron, cover carbon, nothing nitrogen. Iodine is an I, again, fairly straightforward. But helium is an H and a little e. Again, that's fairly straightforward, isn't it? Because they discovered hydrogen, so H had already gone. And lithium is a capital L and a little I. There's no other L in the periodic table, but I wondered if they thought that iodine looked a bit like an L and it might be confusing. So they made lithium an L and a little I. Some of them are really weird, like Mercury is Hg because in Greek, Mercury is hydrogyrum. Tungsten is a W because that's German for wolfram, and lead, this is a fact that I just learned planning this lesson for you, is Pb, which I knew. I didn't know that was because in Latin, lead is plumbum. This joke, some of you already know where this comes from. Do I find jokes about sodium funny? Nah, it's because sodium's symbol is an N and an A, because soda is natron in Latin. Little exercise for you. If you've got a pen and paper, that'd be handy. If you haven't, then you can just do it in your head. The symbols, all the symbols in the periodic table and all chemical symbols are always just one letter or two letters. And the first one is always capital and the second one is always small. So I'll just give you 30 seconds. Decide which one of these symbols you think are incorrect and then correct them, please. Karen, why do you keep using baby letters? Yeah, because I've got a 4-year-old and a 2-year-old. That's awful, isn't it? Oh my goodness, I can't believe I've reached that stage of life where I'm calling cows moo moo cows. All right, so the I should be a capital I. The I should be a capital I. I'm really sorry if that's annoying people. Exactly, you should always have a capital at the start and the second one's always little. The V is correct. The I is correct. I thought that might trick you because you might think that it was a little L. And exactly, that's calcium. Should only be 2 letters. Well done. So now let's look at these numbers. What are they? We're going to look at the top ones, okay? And I'm going to see if you can guess this. So here's an atom of helium, not to scale. And here's the symbol of helium in the periodic table. What do you think that that little 2 might mean? Have a look at that helium atom. What is that 2 telling you? I'll show you another one so that you can do a bit of guess who work. So this is lithium. The top of lithium, the number is 3, and this is a lithium atom. Oh. Carbon is a 6, and that's a carbon atom. What might that number be telling you about the carbon atom? Here's a beryllium. And the number at the top of that is 4. So what is that 4 telling you? Well done if you spotted. It's the number of protons, yeah, because as we discussed yesterday, last week, it's quite easy to take electrons off atoms. So these are the electrons whizzing around the outside. You can take them off, you can add them on. That is still an atom of beryllium. But if you change the number of protons, then you change what the atom is, you change what the element is. So the number of protons is a really important number to know about an atom. And also, yes, some atoms do have different numbers of neutrons. Like a carbon atom could have a varying amount of neutrons. So the proton number is always the same. So that's what that number is. It's the number of protons, and the posh word for the number of protons in an atom is the atomic number. So in your periodic table, you've got all the symbols of the elements, and you've got all their atomic numbers as well. Do not confuse this with atomic mass. Atomic mass is how many protons and neutrons all together. So electrons hardly weigh anything. So the atomic mass is kind of how much the atom weighs. So lithium has got an atomic mass of 7, and you quite often see another number on the bottom of your symbols in the periodic tables. We're not really going to talk about that today. The number at the bottom is like atomic mass. It's like an average amount of how many protons and neutrons it's got, but I think we've got enough to deal with today. All right, you are getting a story time, okay? Because actually, even some GCSEs questions will ask you a little bit about who invented the periodic table and the history behind it. So we're going to look at that in a story. The year is 1817. Human beings have invented batteries, steam trains, and cans. But protons and neutrons have yet to be discovered. And weirdly, can openers have yet to be invented. What we do know is that there are substances that can't be split into smaller pieces. So we are calling them elements. And there are about 63 known elements in 1817. Now, humans being humans, we decided that we're going to try and organise these elements. What a brilliant idea, scientists say. So in 1817, a German chemist called Johann Dobereiner, with apologies to anyone who knows how to pronounce German words, he studied how heavy the different atoms were, and he noticed something weird. You can arrange them, or lots of them, into groups of 3. For example, here we have lithium and sodium, and potassium. Now, you can group those into 3 because they all react when you put them in water. But lithium reacts a bit, sodium reacts more, and potassium reacts a lot. You should look that up on YouTube afterwards, actually. If grown-ups want to note down lithium, sodium, potassium going into water is quite a common classroom experiment. And lithium is the lightest, and potassium is the heaviest, and sodium's in the middle. So there's a bit of a pattern there. And there's another pattern with chlorine, bromine, and iodine. They all react with sodium to form types of salts. But chlorine is the lightest, and that reacts the most easily. Bromine is in the middle, and iodine, which is the heaviest of the atoms, reacts the least. So this German chemist, he called these triads. He found quite a few triads. There was one with calcium and strontium and barium as well. They all have to get really, really hot before they melt. They've got high melting points, but if you order them from the lightest to heaviest, then they melt at slightly lower temperatures as you move along. So, you know, everyone was pretty pleased by this. It was quite interesting. The only problem was the method didn't cover all the elements. And also, like, we kept discovering new elements, and they didn't fit the pattern either. So sadly, it's not what we learn now. It did inspire a lot of scientists to try and order the elements according to their atom's weight, but it just didn't ever quite work out. And then along comes, in 1869, Dmitri Mendeleev, name you should remember. He was a chemistry professor at St. Petersburg University in Russia, very famous university. He was a very hard-working chap. He wanted to write a chemistry textbook because he couldn't find any good ones. He thought, I'll just write one for my students. But he needed a way to display all the elements. So he wrote all the elements' properties, that just means how they behave, like melting points or whatever, on bits of card, and he moved them around until he realised that actually if you put them in order of weight, you did get a sort of pattern. So he started grouping them together. And can you see, this is genuinely what he noticed, that not metals that were very reactive, you had one of those, then straight away after you get a light metal that was really reactive, and then you get a light metal that wasn't very reactive, and these were all going up in weight. But actually that wasn't why we have to remember his name. He did a couple of really clever things. So the first thing that he did is more an English thing. He just marketed it very well. He was very confident. He didn't say, oh, I sort of found this pattern. He said, guys, here's a new scientific law, and this is a periodic table that explains it. So people took notice. The second thing he did, which was brilliant, was where the pattern didn't quite work, he left a gap, thinking, oh, well, that must just be an element that we haven't discovered yet. And in his lifetime, sure enough, we discovered the light metal. It wasn't very reactive. It was absolutely an element that he'd predicted would exist. And actually, a few years later, we discovered 3 elements that absolutely matched his predictions and fit into the spaces that he'd left. So people really started paying attention. And the third thing that he did, which again, just incredibly confident, was, yes, he'd ordered the elements by weight, by mass, but if that didn't quite work, he just moved it to where it fit his pattern, because he was really confident about his pattern. So for example, we see here that iodine is slightly lighter than tellurium. So in the periodic table, if you just arranged it all by mass, by weight, iodine should be there and tellurium should be there. But Mendeleev noticed that tellurium behaved in a similar way to all the other elements that he'd already put in his group 6. And iodine behaved a lot like the elements in group 7. So he didn't worry about it. He just switched them over. But, in the 1890s, a British chap called William Ramsay discovered 5 new elements. Here they are. Helium, neon, argon, etc. They didn't really react with anything. They were totally different to all the other elements. Mendeleev had not predicted them. There were no spaces in the table. I mean, some scientists were saying, like, we don't even think these should be in your periodic table. Maybe his table was wrong. Wrong, 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 wrong. Is this the end of Mendeleev? Ah, no. After a little bit of work, the scientists realised that these new noble gases, as we call them, they actually fit absolutely beautifully onto the end of his periodic table as a whole new group. So we've discovered these noble gases, and rather than prove Mendeleev wrong and we have to start again, they actually became proof that this periodic table really was a brilliant thing. So later on we realised, because we had the means to look more closely at atoms, that the elements were actually ordered, and Mendeleev had really done this, it's incredible, without knowing about protons and neutrons, that he'd actually ordered them by the number of protons that were in their atoms. Now, strangely, he did not receive a Nobel Prize for his work, but if you look very carefully at the periodic table, one of the elements might sound familiar, and there's far fewer periodic table elements than there are Nobel Prizes, so maybe that was the greatest prize of all. David Thomas, thank you. Yes, Emma, they are also called inert gases. Yeah, the Nobel gases are also called inert gases because, well, we certainly used to think that they were totally inert, that they didn't react with anything. Actually, if you look it up, there's some quite interesting cases where we have persuaded them to react with things now. But so here's the bit that if you were in, say, year 7, like Lilia at school, you would learn that these things going down are groups. I've got a version of the periodic table here which numbers them from 1, 2, 3, all the way up to 18. You will usually see them as groups 1 and group 2. These are the transition metals, which don't have a group, poor things, and then that's group 3. That's group 4, group 5, group 6, group 7, and then as we've seen, the Nobel gases sort of came along at the end. Sometimes they're called group 8 and sometimes they're called group 0. Chemistry, far more complicated than rocket science in my opinion. And then these rows going across, these are called the periods. So the groups and periods both have trends, but we tend to focus on the trends in the groups. Right, now I hope you remembered all that. That was a lot of information, and I've got some questions for you. You ready? You can answer one of them, or you can try and answer all of them. I'm going to give you a minute. So they're sort of ordered by challenge, but it's entirely up to you. Like, some of you will be much younger than others. Some of you might have had some formal lessons and some of you won't have. So yeah, see how you get on with these. I'd like you to tell me, using this bit of the periodic table, what is the symbol for germanium? How many protons does a nitrogen atom have? And group 7 elements get darker as you go down the group. So which group 7 element is the lightest colour? These are all the kind of questions that you could get that in a sort of very start of a GCSE paper, or more likely a kind of year 8 or 9 end of year exam. But I'm just doing school speak because I'm a school teacher. Let's go over it very quickly. So yes, the symbol for germanium is G, a little e. Don't forget, if you were writing that down, you probably wouldn't get a mark in an exam for a capital E. But a nitrogen atom has 7 protons, well done, and fluorine would be the lightest colour, and then bromine would be the darkest colour on this list. All right, have a go at these ones then. How many protons does helium have? What's the symbol for arsenic? And what is the atomic number of oxygen? I'll try and catch you out here. 7. Oh, you mean the words at the bottom? Yeah, well, that's okay. It's just helping you to find your way around the table. All right, let's give you the answers to these. Well done, a helium atom has 2 protons. I thought you might get a bit confused because it's in group 0, but no, I have not managed to trick you there. The symbol for arsenic, come on, if you were panicking in an exam, you might have put AR, but well done. I think you all saw that it's AS. And the atomic number for oxygen, I've put in the relative atomic mass to try and confuse you. Most of you are saying that oxygen has 8 protons. All right, and here we go. So, just 3 more level questions then. Which element's atom has 11 protons? Transition metals don't belong in a group. Name a transition metal. And the group 1 elements get more reactive as you go down. So please name an element less reactive than lithium. Yes, well done, Joe. Oh, Joe, I caught you out. Good. Oh, and I caught Dawn out. So the atomic number, again, it's hard because it's kind of a game, a memory game. Oxygen's atomic number is how many protons it's got, which is the number at the top. The way I sort of remember it is that the number of protons defines the atom. Like, it's the number of protons that tells you what atom it is. So atomic number is how many protons, and atomic mass number is like the mass of the atom. But that was a mean one. I can't have you getting all the answers right, or I would feel like the lesson was too easy. Okay. It is sodium that has 11 protons. Transition metals, the one on this page is scandium. What a great name, scandium. And if the group 1 metals elements get more reactive as you go down, then it's hydrogen that is less reactive than lithium. And sodium is more reactive, and potassium is even more reactive. Like I say, look up a YouTube video of them being dropped into water. And just 2 more questions for you then. Just trying to phrase it all different ways. The only metal that is a liquid at room temperature has 80 protons. What's its name? And what is the atomic number of zinc? Mercury has 80 protons, and that is the only metal that is a liquid at room temperature. That's why you get it in your thermometers, because when it gets warm it expands and handily goes up a tube. And the atomic number of zinc is 30. So atomic number is the number that tells you what the atom is. So there are 30 protons in an atom of zinc. All right then, in conclusion, did you remember from last week? This is what you needed to know to get through this lesson, really. Stuff made of only one kind of atom are called elements, and different atoms have different numbers of protons. And hopefully this is what you've picked up on this lesson. You don't need to remember it all, but you should feel like you understand it now, really. The periodic table is a list of all the elements. An atomic number is the number of protons in an atom. The elements were arranged by atomic number from the smallest to the biggest. And could you tell me what the groups and the periods are if I asked you? And maybe you could even explain how the elements in the same group have similar properties. Hello. I want to explain to you why those DJs in Florida got suspended, like nearly got sacked, because they they told everyone that, what was it, dihydrogen monoxide was coming out of their taps, and people listening like panicked and started calling the water board, and there was like chaos in the streets. Last week we learned that di is the Greek word for two. Now mono means one, so it was an April Fool's joke. They did that story on April the 1st because dihydrogen monoxide is water. Good joke, but it was also a way of sort of saying to people, like, it's important that you have a bit of a science education, because sometimes words of chemicals sound really scary, and actually if you do a little bit of research, it's not that scary. Right, folks, thank you so much for joining me today. I'm having so much fun planning these lessons. I used to do over lockdown a kind of more interactive, like you do an experiment with me and there'd always be a story time kind of lesson in this slot. I've moved that now to Thursdays at 6 o'clock and Sundays at 9:30. So if you want to see me on my camera phone doing experiments and reading out like news stories of the week and doing dinosaur of the week and this kind of thing, then that's Thursdays at 6 or Sundays at 9:30. It doesn't matter, it's only numbers, but I've got like 160 likes to go or something before I get 10,000 likes on Facebook. So if you haven't liked my page, I would really appreciate, for sort of stupid pride reasons, you liking my Facebook page. That would be awesome. All my lockdown lessons are on YouTube, so if you want to go to my YouTube channel and subscribe and watch all my adverts, that would be super sweet as well. Right guys, I'll see you soon. Bye.